So we're going to hit week 9 and focus on this hour. We're going to be doing examples over and over again. We only have 2 topics left to go. 2 topics. Well, maybe I'm lying. Maybe 3, but 2 really. One is integral lag compensation, or lag compensation. We're going to start that today. I'm going to show you an example of how that's used. The video is already made. It's on the website. So if you looked at the video before the class, it might not have made any sense. What we're going to talk about is how to build an integral lag compensator that gives us steady state error that we want, which is usually 0 for a step input. We usually, on our outer tracking loop, want the output to follow the input, period. No matter, even if the plant changes. Okay. So this is my secret. If you've ever read anything by me, or when I taught 320, my motto is 320 was making TEAPOTS fly. So if you understand what we're going to do today, you can make a TEAPOTS fly. Because once we build a control system properly with proper loop shaping, the control system doesn't care what you put in it. So if I build an autopilot for an F4 and you want to sell it to the 747 people, go ahead. It'll work on anything. Not within limits, obviously, but that's the goal. Making TEAPOTS fly is pretty much the goal of control theory, and we call that robust control. That means I can take the plant and change it drastically. I can replace my aircraft with swept wing, or change the tail, or change the propeller, or change the size, or make variations of it, and all the control systems, the avionics, are going to work if they're robust. So that's a big goal. That's a huge goal, which we're just going to introduce today. But basically, that should be the goal of 320, is to make TEAPOTS fly. So there's a measure for specific measure, and it's called a loop sensitivity, which we'll also introduce today. So the loop sensitivity is 1 over 1 plus GH, where, as I keep telling Zach, S equals J omega, right? You convert that into a complex number, and you do the Bode plot, and that tells you how sensitive your control system is in the loop closure to percentage changes in the plant. So if I have a 10% change in the G of H in the plant transfer function, GH, my sensitivity says how much that's going to affect the output. So you want sensitivity to be low. Minus 20 dB, minus 30 dB, below the 0 dB line. Low sensitivity means you're making the TEAPOTS fly. Here's the catch. And this is why Bode is a genius. Bode says I can make my sensitivity low only over a certain part of the integral of 1 over 1 plus GH. Another part of that frequency range has to be such that the total integral equals 1. My integral has to be equal to 1. So if I have low sensitivity in one part of my frequency range, which is what I want for control, I'm going to have high sensitivity somewhere else. Can't get away from it. So this is a problem. We want our high sensitivity to occur past crossover. Our high sensitivity occurs past crossover, where we've rolled this thing off and it's not going to respond. And we want the low sensitivity to occur below crossover. Kind of makes sense? Okay, these are some control concepts that are fairly advanced. I don't even pretend to go into the reasoning behind them. But there's a great video, Bode lecture that was given about 20 or 25 years ago, and I've still got the website for it, so I will send that website out. And there are 3 principles given. So if you give me those 3 principles on your next readiness check, I'll give you 5 points per principle. There are 3 principles that if you violate, you're going to end up with trouble when you build controls. So give me those 3 principles, or have somebody watch that video, and it's a long video, so you have to kind of make sure that you're not violating those 3 principles of control when you try to make a TEAPOTS fly. You get a stable system to follow a steady state error, or steady step with no error, if it has an integrator in the forward loop. If you put an integrator anywhere in the OLTF, then the feedback signal will follow the input. The feedback signal will always follow the input if there's an integrator in the path, as long as the system is stable. So I'm going to give you now a system of why we're going to have high gain from making TEAPOTS fly. We know that the closed loop transfer function, CLTF, equals GH over 1 plus GH. Now I'm using the feedback signal up. That's the feedback signal. GH times 1 plus GH. Or your H is equal to 1. Either way you want to do it. If I make the gain very high on G, so if I put a K in here, if I put a K in there, like the root locus gain, and I make K very, very large, then what do I get? The 1 gets dwarfed by KGH, and I get what? 1. Where's the plant? Where's the plant? Plant's gone. I put a teapot in there. You see it? If I make the gain high, I can put a teapot in there, and it will fly with my control law. This is the robustness thing. Now, what Bodie says is, all right, I'll let you do it in one frequency range, but it's going to cost you in another frequency range. So we're going to take it to follow low frequency, step input in a steady state. Steady state is low frequency, step input, low steady states. That's what we wanted to have. So if I put an integrator somewhere in that open loop transfer function at low frequency, that, I mean, everybody's going to be picking on you. How do I get it? S equals what?
J omega.
S equals J omega. As omega goes to 0, what happens to this? Blows up, yeah? Blows up. So I get my high gain and low frequency if I put an S in that loop. That's what we're going to do. That's called the integral lag compensator right here. S plus omega ILC over S, and we'll decide how to pick this in a second. What's the penalty? The J. What does the J cause me to happen to my Bodie plot? How about the phase? What happened to the phase angle when I put the S in?
90 degrees.
90 degree loss. I lost 90 degrees of phase. So if I've got 60 degrees of phase margin at crossover, what has the S done to me? It's given me minus 30 at crossover. It made the system unstable. So I have to take the 90 degrees out. Yes? How do I take the 90 degrees out? I put a 0 in to take the 90 degrees out. And I want the 90 degrees to come out by crossover. So I pick my break frequency for the 0 to be what? 1/10 the crossover frequency. Yeah. So if I pick this omega ILC less than omega bandwidth or omega crossover over 10, don't forget that's a predictor of omega bandwidth over 10. So we're really sticking bandwidth in there, but we're using crossover. If I make my integral lag compensator 0 less than omega C over 10, it will hit 90 degrees by crossover. So I will take out the minus 90 when I get to crossover and keep my same phase margin. Now, double E, if he was in the class, he'd say, wait a second, you put an amplifier in there, that thing's going to catch fire like it did in your thesis when you set fire to your analog circuit board. Well, yeah, but you can approximate this integrator. I don't have time to show you how to approximate this with a passive device. You can build a passive circuit to pretend it's an integrator that won't catch fire. Digitally, I'm going to close the outer loop. I'm going to close this outer loop again through the CAS. I'll close the outer loop over here. And right here, I'm going to put some gain. We'll call that KR. And then I'm going to put S plus omega over S. And then this is going to be my RCOM on the outer loop. And what I'm saying is that this is going to give me high gain at low frequency. How can I verify that? How do I do the Bodie plot? What do I change S into to do the Bodie plot? J omega, right? So this S equals J omega. What happens when omega goes to 0 on this guy? So is infinity high gain at low frequency? Absolutely. So the integral is going to guarantee you steady state, right, if your system is stable. Unfortunately, the S is going to carry with it what angle? That J in the denominator is going to give me what angle? Kevin? 90. It's going to wipe out 90 degrees of phase. Yes? So if my phase margin was 60 degrees at crossover, what's my phase margin going to be at crossover because of that 90 degrees in the denominator? Minus 30. I will be unstable if I just put that S in the denominator. So I got to take that angle out. Right? I take the angle out with the 0. And the break frequency for the 0 has to have a certain value so that it takes the 90 degrees out by crossover. Therefore, this break frequency over here, this omega ILC there, the integral lag compensator, has to be less than or equal to the crossover frequency over 10. Bahij, I know you know the answer to this. What does the angle start for this numerator? What does the angle start going to plus 90 in a numerator? At 1/10, yeah? Where does it get to 90? 10 times, right? 10 times. So 10 times omega ILC has to be less than the crossover. If that holds, I will not affect my phase margin. Now that's what I want you to see out of this whole class, what I just said. So look at the video tonight. I'm going to say it one more time today, and then tomorrow night, if you don't understand what I just said, come see me, right? You want the break frequency for the integral lag compensator, right, to be less than or equal to the crossover frequency over 10. Because if that's the case, you will not affect the phase margin. Your system will remain stable. This holds only, high gain and low frequency only holds if your system stays stable. This guarantees my system stays stable, so I can fix my steady state margin. So since I picked my bandwidth to be equal to 3 on my inner loop, what am I going to want to pick my crossover frequency to be? 0.3, yeah? So I'm going to have S plus 0.3 over S. That should keep me stable, keep my phase margin, right? And give me 0 steady state error.